Hello everyone. First, I would like to thank the organizers for giving me the opportunity to present my methodologic work during my PhD. So the aim of this work is to explore the possibility of representing continuum wave functions with Gaussian functions, and then apply results to some collision processes involving molecules. The idea is to somehow use some quantum chemistry tools to extend collision methods developed initially for atoms. So today I will present first a comparison between real and complex Gaussians. Then I show that the method that we use to optimize Gaussian sets, and then some applications to molecular photoionization, and finally a short summary. So real Gaussians are widely used in quantum chemistry and molecular physics as a basis set to obtain electronic wave functions where the linear coefficient Ci and the nonlinear exponents alpha I, for example, can be optimized by a variational method. And they are widely used mainly because they lead to analytical integrals, and in general they are applied in bound state calculations. As an example here, I show the radial part of the first excited state of the hydrogen atom in terms of the radial distance. And as we can see, we can feed this function easily with 10 real Gaussians. Let us now move to the continuum wave functions. Here, for example, we have the well-known regular Coulomb function for a angular momentum equal 1 and wave number equal 2 atomic units in terms of the radial distance. And so representing this kind of function with real Gaussians is very challenging because of the non-decaying and oscillating behavior of these functions. So the alternative that we propose in this work is to use complex Gaussians. Complex Gaussians, that's to say Gaussians with complex exponents where the real part of the exponents is positive, so the Gaussians still integrable. So this kind of functions have intrinsically an oscillating behavior, and this is why it's we can expect that they will be better in representing oscillating function. Here, for example, we present a nodeless real Gaussian, which becomes very oscillating just by adding an imaginary part to the exponent. So now I'll show the method that we use to optimize Gaussian sets. We wish to represent one or more functions with a set of real or complex Gaussians in a finite radial box. So the idea of the method is to minimize the difference between the objective function and the Gaussians in on some discretized grid, where we optimize the linear coefficient Ci by a least square method, and we optimize the nonlinear exponents with a true-Stresian method, and we iterate over these two steps until achieving some convergence criteria. As an application here, we consider a set of regular Coulomb functions, and we fit this set up to a distance of 25 atomic units with either 30 real Gaussians or 30 complex Gaussians. And these functions are the solution of the radial Schrodinger equation in the case of hydrogen, and they are analytical, and we we can, and they have a lot of application in collision methods. This is why here we choose to fit a set of regular Coulomb functions. And now we take one function from this set. Here we have the exact function, and here we have the perfect fitting with complex Gaussians, and here we have the fitting with real Gaussians. So here both real and complex Gaussians seem to be very good in the fitting box. However, by looking for an extended range, we see that real Gaussians fail totally outside the fitting box. In fact, because of the nodeless nature of real Gaussians, they diffuse outside the fitting box with very large amplitude. And of course, this non-physical behavior may lead to serious problems in the calculation of transition matrix elements. And another problem of real Gaussians is the ill-conditioned coefficient, which also will lead to numerical problems. Fortunately, for the case of complex Gaussians, we don't have this kind of problems, and so we can use them to collision processes. So as I said in the beginning, the objective is to apply the complex Gaussians to some collision processes involving molecules where the molecule is ionized by particle impact or photon impact. But in this work, we will show results to molecular photoionization. A very important quantity, and which allows to compare theoretical model and experimental data, is the cross section, which is a measure of the probability of ionization. And the cross section is given by the transition matrix element between initial and final states. And in this work, as a first step, we consider that the initial state of the molecule is given by a monocentric expansion over slighter type orbitals. And so by representing the final state with the complex Gaussians, the cross-section becomes analytical. And in the monocentric expansion, the angular integrals are performed in a closed form, and they lead to the well-known selection rules of the dipole approximation. What is interesting is the radial integrals. So the radial integrals are given with the radial term of the continuum and the radial term of the initial state. And by representing the radial part of the continuum with complex Gaussians, these integrals become analytical, and they are given with in terms of the optimized coefficients and exponents of the Gaussians with a special function. And in consequence, the cross-section also becomes analytical and very easy to compute. So we applied this approach to several molecules where the molecular orbitals are optimized by Moccia, and the ejected electron is described by a model-centered potential. And in this work, I will show two results for water and methane. Here we will show the results only in the velocity gauge, but we perform the calculation in length gauge also. So here I show the cross section in terms of the energy of the incident photon. And here we have the results obtained with the complex Gaussians. So to check the efficiency of these results, we calculated the cross-section also by performed the integrals numerically, and we get the same results up to few percent. And a comparison with experimental data show that the theoretical results are pretty good. Now we consider the photoionization of methane, also in the ground state. And similarly, the numerical integrals affirm the reliability of complex Gaussians, and a comparison with experimental data show that our theoretical results are reasonable. And here I should emphasize that the objective is not, for the moment, the objective is not to reproduce the experimental data, but what is interesting is that complex Gaussians are reliable and they give exactly as numerical integrations. So in summary, we have written a robust code to optimize real and complex Gaussian sets for continuum wave functions, and clearly we see that complex Gaussians are more efficient than real Gaussians in representing oscillating functions. And once we have the optimized Gaussians, we can easily calculate molecular photoionization in a monocentric expansion. And now we are working on generalizing to the multi-center case. So the initial state of the molecule will be given by an expansion over multi-center Gaussians. And we expect that this will ameliorate the results and allows us to study the photoionization of large molecules. Thank you for your attention.
Well, thank you very much, Abdallah. You were on perfect timing. So we have 3 minutes for questions. I can see one here on the chat. Can you explain briefly how do you fit the exponents? Can you please explain?
I'm trying to find the question.
I can repeat it. Can you explain briefly how do you fit the exponents?
Okay. So to find the better set of exponents, what we do is so first we choose the continuum with the set of continuum wave functions, and then we minimize the difference between these wave functions, or of course the radial part of these wave functions, and the combination of Gaussians. And first we choose an initial guess of the exponents. Then we we optimize the coefficient by a least square method, and then we optimize the exponents by a quadratic approximation algorithm that which is known by the name of Bobika, and we iterate over these two steps until achieving some criteria for on the difference, for example, or on the time of calculation.
Okay, is Dario satisfied with the answer, or does he want some more explanations or any other questions? Dario says he's okay. Are there any other questions? We still have 30 seconds, 1 minute. No? Well, I'm not going to ask questions because I think I understand what Abdallah is doing. Okay, so thank you very much, Abdallah. We can move on to the next talk.